Hello and welcome to this practice test for physics. Today we are going to be covering one chapter in physics. The chapter is types of motion. So let us look at some of the important questions that have appeared several times in previous exam papers in this chapter. So let us start with a series of 1-mark questions. So there are 3 1-mark questions that we will be looking at. The first one, let us focus on the first one. Give 2 examples of imperceptible motion. Now, what is the meaning of imperceptible motion? Let's discuss that. Please write down the question before I give you the answer. So the first question is asking for 2 examples of imperceptible motion. What is the meaning of the word imperceptible? Something that you cannot easily observe or something that you cannot notice. ಅದು ನಮಗೆ ಕಣ್ಣಿಗೆ ಸುಲಭವಾಗಿ ಕಾಣಿಸೋದಿಲ್ಲ ಅಥವಾ ಗೊತ್ತಾಗೋದಿಲ್ಲ. Imperceptible is it is very hard to notice or observe. So for 2 examples of imperceptible motion, one example is all the molecules of any solid are constantly vibrating. You may take the molecules in this board. You may take the molecules in my clothes. You may take the molecules in the walls around you. Those molecules are constantly vibrating. But that motion, that vibration is imperceptible because we cannot see it. We cannot observe it easily. So that is one example. So the first example is the molecules of any matter around us are in a continuous state of vibration. So all the molecules in any matter that you see around you are in a continuous state of vibration. But it is imperceptible because we do not see it. We cannot see it easily. What about another example? You have learned, you have studied that all the land on Earth is made up of tectonic plates. There are plates on the Earth, on the globe, which are constantly moving. And when 2 tectonic plates rub against each other, earthquakes are created. So the country of India is also on a tectonic plate. These tectonic plates are constantly moving, but we do not realize that there is this movement. So that is another example. The movement of tectonic plates on Earth. Both of these are examples of imperceptible motion. The first one is molecules of any matter around us are constantly moving, but we can't see them. We can't observe it easily. That is one example. All the land on Earth is on tectonic plates, and these tectonic plates are constantly moving. That movement is very slow, and we cannot observe it. That is another example of imperceptible motion. So these are 2 examples of imperceptible motion, and that is the answer to the first question. Now let me go to the second question, and I will give you a chance to write down the question, and then we can discuss the answer. Write down the second question. Mention two applications of simple harmonic motion. And once you write the question down, we can discuss the answer. So the question asks for two examples of simple harmonic motion. This is our second question. So one example of simple harmonic motion that most of us would have seen is the pendulum of a clock. You may have seen a clock. This pendulum goes back and forth. And that back and forth movement of the pendulum allows the clock to tell time correctly. So the simple harmonic motion of the pendulum allows us to accurately measure time in a clock. So that is one application of simple harmonic motion. The simple harmonic motion of a pendulum is used to track or measure time in a clock. That is the first example of an application of simple harmonic motion. What about the second example? The second example would be where tuning forks are used in order to tune musical instruments. Tuning forks are used to tune musical instruments. So our second example is tuning forks are used to tune musical instruments. Tuning forks execute simple harmonic motion. Many of you may have seen tuning forks, but I will show you a couple of tuning forks right here. This is a tuning fork, and you can create vibrations in them. And these tuning forks, there are two of them, they create sounds of different frequencies. And such tuning forks are used to tune musical instruments. And these tuning forks, when I hit them like this, they execute simple harmonic motion. So these are the two applications of simple harmonic motion. So let me show you the third question, which you can write down, and then we can discuss the answer. So please copy the third question, which is write the equation that shows the relationship between time period and frequency of a wave. So write down the question and we will discuss the answer after that. So the question asks for the relationship between time period and frequency. The relationship is time period is 1 divided by frequency. The time period is usually expressed in seconds. So the time period is usually expressed in seconds, and the frequency is usually hertz, H-E-R-T-Z. Hertz means so many cycles per second. So the relationship between T and frequency n is T is equal to 1 divided by n. And that is the answer to the third question. I'll give you some time to write this down before moving to the next question. Let's look at the next question. The next question is a 2-mark question, and it's a problem that you have to solve. The wavelength of a wave is 3 meters. 4 waves per second pass through a fixed point. Find the velocity of the wave. So I will give you some time to copy the question, and then I will try to solve it on the board. So this is the first 2-mark question. This is a question where the wavelength of the wave is given, and the wavelength of the wave is 3 meters. And the question says that 4 waves pass through a fixed point in 1 second. So 4 waves per second means that the frequency of the wave is 4 cycles per second. The frequency is measured in hertz. This means 4 cycles per second. The velocity of the wave V is equal to lambda, which is the wavelength, multiplied by the frequency, which is remember, velocity has to be expressed in terms of meters per second. And we multiplied the wavelength of the wave and the frequency to get the velocity of the wave. This is the answer to the question. Please write that down before we move to the next question. The next question is also of a similar kind. I will show you what it is. Please write the question down. The time period T of a transverse wave is 0.1 second. And the distance between 2 consecutive wave crests is 8 meters. What is the velocity of the wave? Let us discuss it. I will write the answer on the board. This is a problem where the time period t is given as 0.1 second. And what else is given in the question? The distance between two consecutive wave crests. So what does a wave crest mean? If this is the wave, this is a crest. This is also a crest. This is one crest and this is the next crest. The distance between the two crests is the wavelength. So when they say that the distance between two crests is 8 meters, it means that the wavelength of the wave is 8 meters. So lambda is 8 meters. In order to calculate the velocity of the wave, we will need frequency and wavelength. But it is not the frequency that is given, it is the time period. So we use the relationship T is equal to 1 by N. T is the time, N is the frequency, and we want frequency. Interchanging the two, you get frequency is equal to 1 by time period. And the time period has been given in this question. The time period is 0.1. And that 0.1 came from here. So the frequency is 1 divided by 0.1, which is 10. So we now have wavelength as well as frequency. Using these two, we can calculate the velocity So the velocity, the answer in this question is frequency multiplied by wavelength, which is 10 multiplied by 8, 80 meters per second. That is the answer to the question. So write down the next question. What happens to the time period t of a wave if the frequency is doubled? So the time period, what happens to it if the frequency is doubled? That's the question. Write down the question. So what happens to the time period of a wave when the frequency is doubled? Remember that the velocity of the wave is the wavelength multiplied by n. And the relationship between time period t and the frequency is t is equal to 1 by n, where time period is t and frequency is n. So this is the relationship between time period and n. The question is, what happens to the time period when the frequency is doubled? Assume that it was n in the beginning. It becomes doubled. It becomes 2n. So what happens to the time period? So if the frequency is doubled, then time period becomes half. It becomes half the original value. So if the frequency is doubled, time period becomes half. That is the answer to that question. So I will leave it on the board and let you copy it before we move to the next question. I will put up the next question on the board for you to copy. It's a long question, so I will let it remain on the screen for a little while longer. It's a multiple choice question and you have to explain the answer as well. So there are two bodies, A and B, of the same mass. A is moving in a straight line with a constant speed of 10 meters per second. B is moving in a circular path with a constant speed of 10 meters per second. Which statement is correct? There are 4 statements. Which statement is correct? And explain your answer. Once you copy the question, remember there are two bodies, A and B, of the same mass. What is A doing? A is moving in a straight line at a constant speed of 10 meters per second. So we can say A is moving in a straight line at a constant speed of 10 meters per second. What is B doing? B is moving in a circular path. B is moving in a circular path with a constant speed of this is a circular path, and B is moving in a circular path, and the speed of B is also 10 meters per second. The question is, which statement is correct? A and B both do not have acceleration. only B has acceleration, only A has acceleration. Both A and B have the same acceleration. These are the four options, and we have to explain why. Now, what is acceleration? Acceleration is the rate of change of velocity. Acceleration is the rate of change of velocity. Now, velocity may change in two ways. Velocity may change in magnitude, which means velocity increased or decreased, or it may change in direction. Even if a moving body changes direction, we say that there is acceleration. Body A is moving at a constant speed of 10 meters per second in a straight line. Is its speed changing? No, because it is constantly 10 meters per second. Speed is not changing. Is the direction changing? No, it is not changing because it is moving in a straight line. Its direction is not changing. Because the speed is not changing and the direction is not changing, body A has no acceleration. There is no acceleration for body A because there is no change in speed, there is no change in direction. Body B, the speed is not changing, it is 10 meters per second, but its direction is constantly changing. When it is here, it is moving in that direction. When body B comes here, it is moving in this direction. When the body B is here, it moves in this direction. So you can see that depending on where the body is in the circular path, its direction is changing, which means that body B is undergoing acceleration. Body B has acceleration because its speed is not changing, but its direction is changing. That is why A does not have acceleration, B has acceleration. So option D, the last option, is the correct option. If we come to the 3-mark questions, list the differences between longitudinal waves and transverse waves. So copy the question and then we will discuss the answer. So the question is asking for the differences between longitudinal waves and transverse waves. And this is a 3-mark question. Transverse and longitudinal. What are the differences? The first one is that in longitudinal waves, the waves move through a series of troughs and crests. They are moving through a series of troughs and crests. In transverse waves, in longitudinal waves, they move through a series of compressions and rarefactions. So the first difference is that waves propagate as a series of troughs and crests. What does it mean? A transverse wave would look like this. These are the crests. The points at the top are the crests. So these are the crests. This is a trough. This is also a trough. So a transverse wave moves as a series of crests and troughs. What does a longitudinal wave do? A longitudinal wave moves as a series of, the wave propagates as compressions and rarefactions. The wave propagates as compressions and rarefactions. What does it mean? There are areas of low pressure and there are areas of higher pressure. I will show you a short video here to make you understand better what areas of low pressure and higher pressure are. Take a look at this. You can see that as the tuning fork vibrates, it causes changes in the pressure of the air around it. You can see that there are areas of high pressure and areas of low pressure, and these are moving through the air as sound waves. This is what we mean by longitudinal waves moving as a series of compressions and rarefactions. This is an example of compressions and rarefactions. So that was the first difference. The second difference is that in the case of transverse waves, the particles in the medium, so the wave may be moving through water or it may be moving through air. So there is a medium, it could be water or air, and the wave is moving through the medium. The particles of the medium are vibrating up and down, but the wave itself is moving in this direction. The wave is moving in this direction, but the particles of the medium are moving up and down. So in transverse waves, the particles of the medium are moving perpendicular to the propagation of the wave. The wave is getting propagated in this direction, but the particles of the wave are moving up and down in this direction. So they are perpendicular to each other. So that is the difference. In the case of longitudinal waves, the properties of the medium are moving in the same direction as the propagation of the wave. So that is the second important difference. The particles of the medium move perpendicular to the propagation of the wave. In the case of the longitudinal waves, the particles of the wave move particles of the wave move